We now turn our attention to the harmonic oscillator, the arguably most important and certainly also most interesting one-dimensional quantum system, with implications far beyond this setting. Oscillations are a universal phenomenon occurring in all areas of physics, and in particular appear in many relevant quantum mechanical settings, both concretely, as say in the vibrations of atoms in molecules or as part of a crystalline lattice, and abstractly, as in the description of photons as quantized modes of the electromagnetic field. This significantly widens the range of applications of quantum mechanics, and indeed paves the way for its use as a fundamental theory of elementary particles and the forces that these experience. A lot of these aspects are revealed by the mathematical solutions, which we can write down exactly and derive in multiple ways. This will really help us to obtain a comprehensive insight into this fundamental problem. Furthermore, this setting is ideal to introduce a range of concepts that prepare us to then formulate a completely general framework for quantum mechanics, which is the subject of the next chapter. This includes a very general way to condense the probabilistic information into a few really meaningful numbers, the so-called expectation values, which are really just averages over many probabilistic outcomes. And this then leads us to Heisenberg's uncertainty principle. In this context, we will also encounter the commutator, a certain way to compare different observables. I will introduce some very general formulas here, and in the next chapter we will see where they come from. This will be a bit more formal and abstract, but what we will have already by then is some really good working practice with these concepts. The setup is very simple. In the classical setting, harmonic oscillations arise when a point particle of mass m moves under the influence of a linear restoration force that points back to the equilibrium position, which we can set to x equals to 0. You can think of k as the spring constant in Hooke's law, even though no mechanical spring needs to be involved to induce this force. The classical motion then follows from Newton's second law, where the dots denote derivatives with respect to time. The solution can be written as a shifted cosine function, where a is the amplitude of the oscillation, t0 a time where the oscillation reaches its maximum, and omega the angular frequency of this classical oscillation. This angular frequency can be determined by inserting the given function for x into the equation of motion. We can write the second derivative conveniently in terms of the original function and read off omega by comparing the coefficients on both sides. The resulting expression also determines the period of the classical oscillations, t, which is simply 2 pi divided by omega. To formulate the quantum counterpart, we need the potential energy, which we obtain from the force by integration. We then see that the harmonic oscillator simply describes the motion of a particle in a parabolic potential. We can set the integration constant to 0, as it can be absorbed into the total energy. Furthermore, we express k in terms of the angular frequency, which we determined above. With this expression, we can then again write down the Schrödinger equation. We again look at the stationary case with a fixed energy, and on the right-hand side we combine the potential energy with the usual kinetic energy. I also write down the corresponding Hamiltonian for later reference. Note that for any given energy E, the classical motion is bounded in space in accordance with the oscillation amplitude A. Based on our previous experience with our earlier examples, we expect that in the quantum problem the wave function decays outside this range. This will indeed again be the consequence of our boundary conditions, which require that the wave function becomes vanishingly small when x becomes very large. So now the particle experiences forces, and hence the solutions will no longer be plane waves. Nonetheless, we can find a simple solution of this problem when we write the wave function in an exponential form. We can work out the second derivative of this using the chain and product rules and insert this result into the Schrödinger equation. This now allows us to match up different terms. In particular, taking S as a quadratic function with a suitable curvature, the first derivative is linear. In the Schrödinger equation, this term appears squared, and this then cancels with the term with the potential energy. This leaves the second derivative term, which is constant, and by comparing it with the other side, it determines the energy. So for this choice of the function S, which determines the wave function, and energy E, both sides of the Schrödinger equation are identical, which is really what we mean by solving this equation mathematically. Furthermore, the solution that we found is also physical, as the wave function indeed decays rapidly when x becomes very large. As we will confirm later, this is indeed the ground state. And its energy almost looks like the Planck rule with an intriguing factor of 1/2. We will understand this better when we have worked out the rest of the states. But for the moment we remain focused on the ground state itself and next have a closer look at the ground state wave function. Mathematically, the function that we encounter here with x squared in the exponent and a negative real constant in front of it is called a Gaussian, which is a really important function in mathematics, in particular in probability and statistics. To understand its properties, I have rewritten it here in terms of a new constant, sigma, that will soon take on a concrete physical meaning. Indeed, we immediately see that this constant determines the width of the corresponding probability density, which is indeed also a Gaussian, and with our definitions takes the standard form as encountered in statistical and probabilistic problems. To analyze the properties of this probability density in detail, we need some integrals. The first one is the famous Gaussian integral, which we will need to normalize the wave function. It can be derived by a standard trick in which we rewrite the square of the integral in polar coordinates. The integral over the angle is uniform, so just gives us 2 pi, while the integral over r can be carried out by substitution. So this gives us pi over a, and the Gaussian integral is just the square root of this expression. To give a precise meaning to sigma, we also need a related integral, which follows by taking a parametric derivative of the definition of the Gaussian integral on the one side and of its closed form expression on the other side. We then find an expression for a modified integral where the exponential function is multiplied by x squared. Okay, so turning now to the normalization of our simplest solution, as always we demand that the integral of the probability density over all space equals 1. This is a Gaussian integral with the constant a that we used in its definition replaced by 1 over 2 sigma squared. The result gives us a condition for the constant c in front of the wave function. As in the particle in the box, this only fixes its absolute value, but we are fine to take the simplest possible choice, where c is real and positive, as indicated here. So this gives us the normalized form of the wave function and the probability density. To extract some useful information out of these expressions, we now introduce the concept of an expectation value. By this we simply mean the average value of an observable that we expect to obtain when we measure it many times. This is of course an experimental prescription, but on the theoretical side, for any observable a, this can be obtained from the probability density p of a by an integral, where p of a plays the role of weights for the different possible outcomes a. When you see this for the first time, this is perhaps more transparent when we have a discrete set of possible outcomes, which we can label by an index n. The average is then obtained by a sum in which these values are weighted by the corresponding probabilities Pn, as I have indicated here. And as we have already seen for energy, quantization can indeed force observables to have discrete values. Later we will also encounter different examples of this. Besides the expectation value of the observable itself, a particularly important quantity is the expectation value of the squared observable. Also known as the second moment, the average of the nth power is just the nth moment. This is because we can combine these expectation values into an important statistical quantity, the standard deviation, written here as delta A. You may well have encountered this in other contexts. In quantum mechanics, with its inherent probabilistic nature, this becomes a central and really useful quantity with rather beautiful properties. As a matter of fact, just as calling our averages expectation values, we again give the standard deviation a new physical name and call this the uncertainty of A. Now, if you have another observable that is really just a function of A, you could of course introduce the corresponding probability density for this, but even simpler, you can just place this straight into the definition of the average. So this is how you would normally calculate the standard deviation with one specific probability density describing all aspects of any given statistical quantity. But in quantum mechanics, all probability densities arise from a single entity. In our one-dimensional setting so far, the wave function psi of x. We have seen this already when we introduced the probability density for momentum. And this gives us a miraculous shortcut, the formula which I give here for our present case of one-dimensional systems, where you place the observable in question into the middle of the normalization integral. So when determining these expectation values, you can get completely around the really arduous exercise to calculate separate probability densities for all the different observables. We will derive this formula soon. It results from a simple general expression that applies to all quantum systems, which we can write down as soon as we have set out the complete theory. But we can already test it here for the ground state of the harmonic oscillator. This will already reveal the enormous utility of this shortcut for practical calculations and give us an early glimpse of the central importance of this formula. So let us now look at some expectation values for the ground state of the harmonic oscillator. We start with position, so can just use our now familiar expression for the probability density in terms of the wave function. Now for the expectation value of position itself, the integrand is positive for positive values of x and exactly oppositely negative for the corresponding negative values of x. So these contributions cancel and this integral actually vanishes. If you want to check this integral can also be evaluated exactly. Note that the fact in front of the exponential function is really just a derivative of the exponent with respect to our integration variable. For the second moment, our prescription leads to the integral that we inferred from the Gaussian integral by taking the parametric derivative. Again with a replaced by 1 over 2 sigma squared. But when we combine all the factors, this simply becomes sigma squared. And so when we insert these expectation values into the definition of the uncertainty, we find that this really just equals sigma, which gives a precise physical meaning to this constant. And indeed, as we mentioned above, sigma naturally determines the width of the corresponding probability density, and we have quantified this now exactly. To obtain the corresponding expectation values for momentum, we now have a choice. We can first work out the probability density in momentum and then apply the standard definition of an average, or we can use the general formula that I've given above. We start with the latter because this gives us the result quickly so that we can first focus on the physical interpretation. But we will also do it in the other way, as this gives us some confidence into our presently still untested general expression for this case, and the result that we will obtain will be interesting in itself. So let us translate our general formula from above to the case of momentum. We simply use the definition of the momentum operator, which involves a derivative. We have been careful to adhere precisely to our general formula. Note that the operator acts on the wave function to its right, but leaves the complex conjugated wave function on the left untouched. But please do not worry about this apparent asymmetry. We will soon understand it based on the general theory. Now we need to take derivatives of the ground state with respect to position, but this can again be done just using the chain and the product rules, so I give you the result here and leave the steps as an exercise. Now, mathematically, the integral for the momentum expectation value has the same form as we earlier encountered for position, just multiplied by a constant, and so we find that this expectation value vanishes as well. For the second moment, we can separate the integral into two parts, and one just looks like the normalization integral, while the other one involves the second moment for position. So we can again recycle our results from above, and what we then get is a really simple expression, h bar squared divided by 4 sigma squared. So this is all we need to work out the uncertainty of momentum, which comes out as h bar divided by 2 sigma. To refer to this back later, I'll give this expression a separate name and abbreviate it as sigma p. Now sigma was just the uncertainty in position, and so we can write down the following relation. The product of the uncertainties in position and momentum is h bar divided by 2. As it happens, this is a really special and characteristic feature of this particular state, the ground state of the harmonic oscillator. Because if you look at any other physical state, for any other quantum system, this product of uncertainties will never be smaller than this value. We can write this down as a general inequality. This inequality is Heisenberg's uncertainty principle. We could derive it now based on some more technical properties of the Fourier transform, but in our general framework it will actually follow from a more general variant of this principle that gives a bound on the uncertainties for any pair of observables, not just x and p. And as it happens, this will relate to the following curious property of the position and momentum operators. When you apply them consecutively to a function, but in different order, then just by the product rule you get two different results, and the difference is really just an extra constant multiplied to the function. And this just involves h bar. Now we can actually define a new operator that is just the difference of these combined operations, and we see that this new operator is just this constant. We call this the commutator and can define this for any pair of observables. It will reappear as an essential object in our general formulation of quantum mechanics, but it is actually also a very useful concept for calculations, as we will see just a little bit later in this chapter when we come to another method to solve the harmonic oscillator. Right now it is more important to realize the physical implications. If a particle is well defined in space so that its position uncertainty is small, its momentum uncertainty must be relatively large, and vice versa. And this is indeed what we saw in our earlier problems. It was one of the points we made when we discussed the particle in the box. There we just based this on our calculation of the probability density in momentum. Here we completely sidestep to calculate this density, but we will do this now. This probability density is defined as the absolute value squared of the momentum wave function, which is the Fourier transform of the position wave function. And for the ground state, that's still, of course, our Gaussian function. When we write this out as an integral, we see that this involves an exponential function with a quadratic term in the exponent, quite similar to a Gaussian integral, and we can indeed bring this into this form by writing the exponent as a shifted parabola. This shift does not affect the value of the Gaussian integral. So we can use our general result, which is then just multiplied by constants and a function of p. And the key point is that this function again takes the form of a Gaussian, but now in p. As a matter of fact, we can write this in terms of the momentum uncertainty sigma p, and then the probability density takes the form of a standard Gaussian, just as we had encountered for position. So if we use this momentum probability density to work out the momentum uncertainty, by the same mathematical steps that we worked through for position, we would simply get sigma p. Just the same result as we obtained from our shortcut. So we have finally verified this result, and furthermore now see very directly that the momentum uncertainty indeed characterizes the width of the momentum probability density. This covers the main aspects of the ground state wave function. As for the value of the energy, we already remarked that it reminds us of the Planck rule, but with this mysterious additional factor of 1/2. To clarify this, we next look at the full solution of the problem, so also at all the excited states. And we will actually present two solutions, a more basic one and a rather sophisticated one, where we adopt two completely different mathematical approaches. Both approaches can be applied to many other problems, including the key problems of angular momentum and the hydrogen atom that we will encounter later in this course. Applied to the harmonic oscillator, they will give us very different insights. Our second approach will require some further mathematical preparations, which are also essential to formulate the general theory. So we first use one method to give us an already complete picture, and present the second method after a short mathematical intermezzo. In our first approach, we simply generalize our steps to find the ground state. So we really focus on the fact that the Schrödinger equation is a differential equation and try to find appropriate functions and energies so that both sides of the equation agree. As a matter of fact, in terms of the mathematics, this is a relatively standard type of differential equation, and what we do here is long well established. As we already have one solution, we try to make use of it and simply modify it by multiplying it by another function, little h, where I introduce a convenient constant alpha into the argument. Note that any function can be written in this way. This step simply helps us to find the solutions. Furthermore, we extract the factor h bar omega out of the energy, so introduce this new constant epsilon, which is just a number. Again, this is guided by our known solution, for which epsilon is 1/2. Now, I again spare you the detailed steps, but we can simply use the chain and product rules to work out the second derivative of this and insert it into the Schrödinger equation. I just give you the results for both steps that are easily checked. After cancelling some common terms, we then arrive at a mathematically really much simpler differential equation for h. Its key property is that some of its solutions are just polynomials, and these will indeed lead to the physical solutions. Indeed, the established mathematical procedure to solve such an equation is to first express h as a power series, where we initially allow it to have infinitely many terms. When we insert this into the differential equation for h, we can compare the coefficients in front of the powers on both sides, and this gives us a simple relation between the coefficients hn. And this allows us to calculate all coefficients recursively. Now, if we assume that the power series has indeed infinitely many terms and look at how they behave for a large index, then they approach the same form as the exponential function of y squared. And even if we then multiply this by our decaying Gaussian, we would end up with a function that does not decay at large distances. So we cannot allow for this. Instead, we need to find situations where the power series terminates. Hence, really it's just a polynomial. Multiplied by our Gaussian, our boundary conditions will then be satisfied. Now, if we look back at the recursion relation for the coefficients hn, we can achieve this by selecting certain values for epsilon, namely 1/2 plus an integer n with the smallest possible value of n being 0. As it happens, the resulting polynomials are really well known for over 200 years. They are called the Hermite polynomials. I list the first few here, as well as a general formula that can be used to generate all of them. This gives you polynomials of degree n, so the degree agrees with the assigned index. Mathematically, these polynomials are one of several classes of so-called orthogonal polynomials, and the occurrence of this word, orthogonal, isn't a coincidence. It will soon reappear in our general formulation of quantum mechanics and be part of the beautifully simple underlying structure that we will then uncover. But in any case, this now fixes the wave functions in our solutions, so let us next look at the energies. As we have determined epsilon, we can write these energies directly down. They are given by h bar omega times an integer plus 1/2, with the integers running from 0. Now we see that the Planck rule really appears when we look at the energy difference between these states. So you can perhaps already anticipate that it really relates to the way the system can change its energy. We will later call these changes transitions. So now to put this all into a picture, what we obtain is a set of equally spaced energy levels that are separated by h bar omega. And when you look at the corresponding energy eigenstates, then we have the Gaussian wave function in the ground state. And the excited states are just this Gaussian multiplied by a Hermite polynomial. Note that these polynomials have exactly n points where they vanish. They have n roots, which here translate into n nodes of the wave function. So this is a feature that we have already seen for the other set of bound states that we have encountered so far, namely for the particle in the box. And it is indeed a strict mathematical feature of bound states in any one-dimensional system. But beyond this, we see that the different states and energies of the system seem to be very systematically related. And this is indeed true, as we will see soon when we solve this problem by a completely different method. But before we do this, we will consolidate our observations by introducing a more formal and really general mathematical language. This will already be the language in which we later formulate the general framework of quantum mechanics. And we will see straight away how useful this language is when we then look at the second method to solve the harmonic oscillator.